Now we have the second speaker of our afternoon session, and it is Felix Kling, who is also Frontiers of Science awardee this year, and the talk will be about FASER experiment.
Okay. Yes. I would like to thank the organizers for inviting me and, well, most importantly, selecting me for this award. So on behalf of my collaborators, I very much want to say thank you. It's a very nice opportunity to come here. I've never been in China. I'm very happy to be here and experience this event. So this talk will be about the FASER experiment, which we proposed in a paper written by 4 theorists in 2017, and which at this point was just theory, an idea, but which, as you can see, actually became reality. And I want to, well, summarize what we proposed in 2017 and that shows a journey on what happened afterwards towards reality. I thought I wasn't sure what audience to expect, so I well try to have a more funny talk with anecdotes and lots of pictures and not so heavy on the technical side. So I hope you enjoy this. Yeah, thanks for everyone for being here. Okay, let's see. Ooh, other way? No. Okay. Does it work? No. Okay. So, as we all know, the LHC is the most energetic particle collider that we have built as humankind. And the main focus is well, study of heavy particles. So, for example, the Higgs boson, which we found, or supersymmetric particles, which we haven't seen yet. And roughly speaking, heavy particles are more or less used at rest, and then they decay roughly isotropically. So you build big detectors around the interaction point that try to cover as much solid angle as possible and see all the various decay products that could come out of these decays of these particles. And the experiments, in particular the big ones, Atlas CMS, were constructed to catch them. But there is another region, which is the forward region, that is not covered by those experiments. So this is a region close to where the beam comes in and out, and there naturally there's a beam pipe and no detector. Just to give you a feeling for what we produce there, well, we produce a lot of hadrons. It's about, for example, 10 to the 17 pions are produced within 1 milliradian of the beam. A milliradian is a little bit smaller than the moon on the sky, but this is still about 10% of all pions produced at the LHC. And most importantly, the most energetic pions, these can get like, well, order 1 fraction of the beam energy. So what we ask ourselves is, well, can we do something with a huge amount of very energetic pions? And the answer is yes, otherwise I would not have been invited to talk about it. Wrong direction. These pions can, kaons and so on, they can decay. So for example, in known particles, for example, neutrinos, but also in not yet discovered particles, for example, dark photon, dark matter, axion-like particles, and so on. These particles would then form a beam in the forward direction. They're very energetic, they have low transverse momentum, so it's a very collimated and quite intense, which would just go, well, in a straight line. Of course, we can't put a detector right here because then we block proton beam. That's not good. And actually, well, Atlas cannot see them. It's perfectly designed to not see these particles. But the LHC tunnel will eventually curve away. It's roughly speaking a circle. These particles go straight. So the idea we had in this paper is to place an experiment here in this beam, but after the LHC has curved away. So this is a paper that has been awarded this award, which proposed the FASER experiment. Here is a screenshot of the paper, and here is myself and my co-authors. We all look a little bit younger than we are now. It's how you imagine theoretical physics to happen. It was originally an idea on a whiteboard in a coffee break after lunch that we then explored more and more until the paper appeared. So sort of the most stereotypical example on how theoretical physics works. I promised a few anecdotes. So the FASER experiment, we actually got the idea when one of us, Jonathan, visited the Star Trek Museum in Seattle. And we were looking for a funny acronym that starts with F for forward. And he saw this FASER gun here. So this is this light gun they have. And he thought, FASER, that's a really good name. We need to come up with an acronym that results in FASER. So we wrote in the paper this acronym records another marvelous instrument that harnessed highly collimated particles and was used to explore strange new worlds. Shortly after, we do the most famous physicists at the time, which is these guys. So Jonathan was invited to the studio of Big Bang Theory. They filled all the whiteboards about it. So at the time we were saying, we talked to them and they agreed that's a good idea. Maybe that helped with approval, I don't know. Okay, so that was basically what we wrote in the paper. Of course, we had way more math and nice figures and so on. But what I want to do is to show you what came out of this paper, what happened afterwards. So the first thing we did is we wanted to find out if this is feasible. So if there is a place where we could put the experiment, because digging a hole is well, highly non-trivial. So the first thing we did is we Googled for a map of the LHC. So this is a map of the LHC. And remember, we want to sort of be in a tangent line of one of those experiments. So we looked at all the interaction points and well, we saw that maybe around here there are some tunnels that maybe could be used. So we looked at a better map. So this is a CERN version of Google Maps. And here's the Atlas experiment. And the red line is where the neutrinos and dark photons would go. We looked if it intersects with some tunnel. And we saw two tunnels, this one here and this one here where it intersects. So this is the LHC here. So you see it curves slightly. This is the SPS. It curves much more. And this here is a injector tunnel from the lab era. It wasn't used for the LHC anymore. They had to build a bigger and better tunnel, but it was still there. So we got very interested in this. So there are two places where one could put it. We talked to Mike Lamont. He's now the head of the accelerator department at CERN. And he actually went down and took some pictures. So this is from, I think, it's from 2017. So he looked and he saw, oh, okay, this is the tunnel where FASER is now. Seems kind of empty. He looked a bit further. So here is roughly where the beam goes. Nothing there, so that's good. He looked a bit further. There was the door here. It said, door definitely closed, cannot be used as emergency exit. Okay, that means that certainly no one wants to walk by here because there's nothing behind. So that was actually very encouraging. So we found that there is a place. Then a little bit later, this was actually on my birthday, the next year, the CERN survey team mapped out where the line of sight is. So where the beam goes, here you can see them work. And they found it very much goes to the tunnel, actually about like 10, 20 centimeter below the concrete here. So we found an ideal place to put the experiment. We were very lucky. This was by far not guaranteed that this is possible. To put the experiment there, let's remind ourselves that the beam of particles, this neutrino beam, for example, or beam of dark photon, is really highly collimated. And I want to show here, this is the number of neutrino interactions that we would expect as a function of well, how far are you away from the beam. So here is the center of the beam. And this circle here, this is now the FASER experiment with a radius of 10 centimeter. And you see that, well, you don't want to be more than order of 10 centimeter away from the beam, otherwise you lose a good fraction of events. So we really want to be close to the beam. It's not very big, it's very small. So what we said is, okay, we need to dig a trench to really be on the beam. And then put the experiment around. So this is a figure from our technical design report. So this is what we envisioned. Essentially, it's a bit like a telescope that looks from 500 meters away through 100 meters on concrete back at the Atlas interaction point that is perfectly aligned with the beam of particles going through. Okay. Here are some pictures on how this was constructed. So one of the first things they did is they put a protection over the LHC, the walkways on the other side. So the worst thing that could happen is that we damage the LHC, and then everyone at CERN would very much hate us. So they put some protection around and a little bridge that we could walk over, so that whatever we do wouldn't interfere with the rest of the program. And then they started to, well, remove all the pipes and whatever there was still around, start to dig a trench. So this was in 2020. This was, I think, right before Corona hit Europe. Yeah, this is where the FASER experiment is now. So how does the experiment look like? So this is what I imagined in 2017. So this is a typical theorist drawing made in PowerPoint. Our first goal that we discussed at the time was a search for new physics. So what we had in mind is long-lived particles. So particles that can travel a macroscopic distance before decaying. They appear in the standard model. Think about pions and kaons. Neutrons and muons, but they could also appear in models of new physics. There are plenty of examples. My favorite one is the dark photon, because that's the first one we thought about. So this one it's like a photon, it couples to a charged particle, it would decay to an electron pair, for example. Could travel, depending on how you choose its parameters, its mass and its couplings, to travel 500 meters, so the distance to FASER. And then would decay. So we essentially see two highly energetic particles, so particles with TeV energies, emerge in empty space 500 meters away from the experiment. And how would we see that? Well, these are two tracks. So I thought, well, then we want a tracker. And I want to see that it's two, but they're highly collimated. So let's add a magnetic field to split them, and we know it's two. Then we can also measure what is the momentum. And let's also put a calorimeter, then we can measure its energy as well, so be a bit redundant. I'd certainly put some front veto to make sure that nothing came in. Yeah, and that would be a very spectacular signal that we couldn't think about anything that would fake this. And as you will see later, we also haven't seen anything that fakes it. The one thing we were a little bit worried about were neutrinos. So neutrinos also go through hundreds of meters of rock and avoid our veto here. However, they interact with materials, so if we have an empty decay volume, that's not really a problem. Also, they typically don't produce electron pairs, but let's say muons and a lot of hadrons, so this can be differentiated. But then we thought, it's not really a background. Let's promote it to a signal. Those neutrinos at the LHC have also never been seen, so we added in a neutrino detector. I'll show some pictures later on, so that we can study these neutrinos, and we found that this is actually very interesting. At the time, I tried to calculate how many neutrinos we expect, And I found that it's very difficult to predict since there are huge uncertainties. And all these uncertainties are associated with interesting underlying physics questions that we couldn't answer at the time, but that we can answer or start to address now with these measurements. So at the end, we decided to add a margin detector. You might ask, why a margin? Well, because the first neutrino physicists that we talked with worked with immersion films, and we asked them, what detector should we add? And they said, unsurprisingly, how about an immersion detector? So, okay. So this is later what we had in the technical proposal. So this was made by my experimental colleagues. It looks way more sophisticated, but if you look closely, it's actually pretty much the same design as what I've showed you earlier in my PowerPoint drawing. So we have an immersion detector, we have a magnet with a tracking system, plenty of scintillators, at the end, electromagnetic calorimeter. Actually, this was relatively cheap because we were lucky we could reuse a lot of components. The electromagnetic calorimeter was donated by LHCb. The tracking system were spare modules for the Atlas SCT tracking system. This was making use of additional components that were lying around in various institute basements that we could use for free. This is a picture of the detector. What amazed me as a theorist most was the amount of cables that stick out of the detectors. I never thought about cables, but you can't see anything else here. But again, same as my theory drawing, at least conceptually. Okay, so the FASER collaboration, last time I checked, or when I made the slide, consisted of 107 collaborators from 27 institutions in 11 countries. And since we are in China, there are 2 or 3 Chinese institutes, I think these here. Really a worldwide collaboration. I never imagined this when we started to write the paper that it would keep so many people busy. Okay, so let me show you some more results and insights into our searches for new physics, which was the primary physics goal at the time when we wrote this paper. Why or what do we look for? Well, we know that we have a standard model sector. We are made of it, and we have studied it in great detail at all the experiments at the LHC and previously. But we also know that there is dark matter, and this could be part of a dark sector that, we don't know anything else about besides that something like this must exist. And typically what we want to do is we want to predict the abundance that we see of dark matter and standard model matter, which we have measured in cosmology. And to make some predictions, we need typically some assumptions on how they interact. If we assume that they don't interact at all, it's very difficult to make any predictions. So typically we have a mediator that, for example, in the scenario of thermal freeze-out, then allows us to predict how many dark matter is still around nowadays. So in the classical times of supersymmetry, this was either the Z boson or the Higgs boson, and then the sector of the neutralino. So particles with weak scale couplings and big scale mass, which happen to predict the abundance of dark matter very well. This does not work so well for white dark matter. So Olli, Lee, and Weinberg said that if you have dark matter with a mass of a GeV or below, the Z and Higgs boson will not be the right mediator. So then you could add a sort of a dark cousin of those, so something like the dark photon, which would be lighter and more weakly coupled, that could similarly act as a mediator and mediate the freeze-out of the light dark matter. What's the phenology of this model? So dark photons actually rise in many scenarios of hidden dark sectors. So it's a massive gauge boson of some broken dark U1 symmetry. It can kinetically mix with a photon, so you have a diagram like this, and if you rotate the basis, you can essentially define or make it couple to the fermions with a small coupling. And like everything in mass that's called epsilon, this must be very small, because otherwise we would have seen it already. So it's very weakly coupled to the standard model. Otherwise, it essentially behaves a photon, just that it's massive and very weakly coupled. So for example, it could be produced in essentially any process that produces photons. For example, at the LHC in pion decays. So if kinematically allowed, you have something like pion goes to dark photon and the photon. The branching fraction is essentially the coupling squared. And if it is not kinematically possible to decay to dark matter, well, it has to decay back to visible matter. So the lightest example would be an electron pair, and that's the signature that we look for. Okay, here is the landscape of the dark photon. So this is its coupling, and this is its mass. The gray shaded region are all the existing constraints. So for example, from resonance searches at bar, this is at high coupling. At low coupling, there were searches for long-lived particles, for example, at Newton experiments like NuCal. What FASER is doing, it's well, more like the long-lived particle experiments at the beam dumps. But since the boost of particles is much higher at the LHC, well, we could probe more short-lived particles. Short-lived means higher coupling. So we could bite into this empty space here from below. And here I show some sensitivity lines for different luminosities. So 1 inverse femtobarn is roughly a day of running. 150 is, well, nowadays roughly a year of running. And you could see that we expected all the at the time to get interesting results after our first day of running. Here also shows we started with a discussion of dark matter, so a target line. So here I assumed that well, the dark matter and dark photon have sort of similar mass, and that shows an Euler-1 coupling constant. You can change these parameters a bit, and it goes up and down a few centimeters on this plot. It's not super sensitive. But it shows that this target line goes right through this sort of empty region here. So this is actually a very cosmologically motivated parameters probe to test the scenario of dark matter. Okay, we have turned on the experiment in 2022, so the beginning of run 3 of the LHC, and in 2023 performed the first search for dark photons. So at this time, we just turned on the experiment, so we didn't really know what to expect. We designed a rather simple and robust and quick to do search for dark photons. So what we wanted is essentially no signal in the front vetus, so nothing comes in. And then we wanted to see that 2 tracks appeared with well, the later scintillators having a signal that's consistent with 2 particles going through, so 2 minimum ionizing particles and a high energy deposit in the calorimeter. So 3 main features, so no signal in the front, 2 tracks, high energy. And we estimated that the background, mainly from neutrinos, should be something like 10 to the minus 3 events, so essentially negligible. And then we looked at the data, and we found no events in the signal region. We actually found no events that were anywhere close, so we were very conservative. We could have, going back here, dropped either of the 3 cuts, either the front veto, the 2 tracks, or the calorimeter cut. So this makes us very convinced that backgrounds are not at all an issue in this region, as we were actually already expecting. So that's of course very unfortunate that we didn't discover new physics, but okay. But we could set limits on the previously unexplored parameter space. So this is shown here, and this agrees very well with the projections that I showed a few slides ago, and that we already showed in the papers that we got the award for. And this probe this interesting thermal relic light. Yes. So this was 30 inverse, or 27 inverse femtobarn. Oh, that we got from Atlas. No, we didn't measure that independently, but since we use the Atlas beam, we can use the luminosity. Okay. More recently, we also did a search for longest particles decaying to photons, so there are no tracks. So this paper, and constrained actually a variety of models. So for example, axon-like particles, 2x-star models, other gauge bosons. Felix talked earlier about the U1B gauge boson that couples to baryon number. We probed this. I think this is this scenario here in the couple hundred MeV range. Some scalars that only couple to up quarks. So actually, many of these benchmarks were proposed by the theory or Pheno community. And I made a personal effort to try to push our experimentalists to probe these ideas when possible. There are many more analyses ongoing or planned, and many more models that can be tested. So this is a figure I made that showed all the, or many, not all, but many of the models that have been studied in the context of FASER, and then the connections to the big problems in particle physics, so the nature of dark matter, the strong CP problem, cosmology and inflation, the origin of neutrino masses, baryogenesis, the hierarchy problems. We can see that longest particles actually probe a large variety of solutions of these fundamental problems that all keep us busy and motivated. Okay, I would like to come to another topic. This is collider neutrinos. In the first paper we wrote, this was more of a background we considered, but as I mentioned, afterwards we thought about it as an additional signal, and as I will show you, there's actually lots of interesting physics behind it. So there's, as I mentioned, a huge flux of neutrinos in the forward direction. They're mainly coming from pion, kaon, and d-meson decays. And this was realized as early as 1984. Alvaro wrote a paper that was called, I can't really read it, but something like neutrinos at future accelerators. So at this time it was future. He talked about the SSC and the LHC. This was a time when papers were written on a typewriter and equations were added by hand. So it's a very old idea. But and it reappeared a couple times in the decades afterwards, but really nothing happened on the experimental side until 2018. So we put a pilot detector in the beam mainly to see what the muon flux was in the Martian detector. We talked to the Martian people. And we analyzed it a little bit later and saw the first interaction candidates. And just to give you a feeling, this box that was like 10 kilograms, it's like a small suitcase, maybe even smaller than that, that saw that. Just to illustrate the potential. Here is a figure that I took from my colleague Jonathan Feng. So collider neutrinos have not been observed by the previous detectors. So these are all the previous big collider detectors like, well, Atlas CMS, but also CDF D0 and the lab detectors. And these were all building-sized detectors that run for decades, cost billions of dollars, and altogether have seen zero neutrino interaction. And then we came with this tiny suitcase-sized detector. We put it in for 4 weeks. It cost $0 because it was recycled parts of another small-scale experiment called DS Tau. That's also small, that one heard of it. And it saw 6 neutrino candidates. And this just illustrates the potential of the forward direction. Of course, this was not a real measurement yet. I mean, we saw 6 candidates, but it was like, I think, around 3 sigma or so significance. But it motivated us to put a real big detector in. Actually, not only us. So there are 2 experiments now looking for this. So there is a FASER experiment that I'm working on, but also other colleagues from S&D at LHC, which are on the opposite side of Atlas, also looking for neutrino interactions. So there are some differences in technology and location, so they're actually quite complementary, and I would say we actually learned quite a bit from each other in the mistakes and advantages, and I think it was very good that we have two. It's always good to have two experiments. Okay, I will of course mainly talk about phasers since this is the one I work on, but the others have done somewhat similar things. So our first observation of collider neutrinos, since we had competition, we all wanted to be very quick, was to not use the neutrino detector, so not use immersion, because it takes a long time. You have photofilms, you need to develop them. It's very time intensive, but instead do something much simpler, namely to essentially look for muon appearance. So if we have a neutrino, essentially we see that nothing comes in, so this front veto stays off, and then neutrino interacts, and you get a particle out, especially a muon, that then goes through the rest of the detector. It's high energy, you can measure its momentum, and then have a muon appearance signature. We spent a lot of time estimating the backgrounds, and we essentially saw that there are something like 0 ± 2 possible background events, mainly from muons coming from the side, maybe scattering in the detector, and then sort of go parallel. This is rather unlikely, especially if it's very central and very high energy, but okay. And the signal is essentially muons coming out of the center of the detector, going sort of very parallel. So this is the figures that we made. So I said we want so this is the energy of the muon or the momentum, and this is the distance from the center of the FASER detector. And large angle muons are typically more on the side and typically more on the low energy side of things, where they scatter more and it's more likely that they change their direction significantly. And our signal would be the central part of the detector and high energy. And you can see that this population, if you extrapolate it in this direction, you don't expect to see much there. Then we unblinded our signal reaching, and we saw that the second population of events showed up, and this is exactly what we expected from neutrinos. We did the statistical analysis. This was 16 sigma above our background expectation, and 16 sigma is a point where, this Gaussian statistic does not make sense anymore, but it's certainly very convincing. So at the time, I predicted 150 events. That was my theory prediction. When we unblinded and saw 153, I was super happy. This was spot on. Yeah. So we also have the neutrino detector. Here's a picture. It's an emulsion detector. It's tungsten plates interleaved with emulsion films. So emulsion films are photofilms. And they have very high resolution. So they have some crystals inside. If a particle goes through, it changes the structure of the crystals. And after you develop the photofilm, it's in a different color, and you can see where the track goes. And these crystals have 100 nanometer size or so you have 100 nanometer spatial resolution. This is pretty amazing. We don't have any other technology that can do this. The downside is, you don't have timing. It's a photo, not a video. That makes it very challenging. Okay, we collected data in 2022 for this box here for 10 inverse femtobarn. And in the first analysis, we have analyzed 100 kilogram of it. It takes a long time. So you have the emulsion films, you take them out. Then you need to develop them. It's 700 films. You put them in some chemicals in a dark room. You have a bunch of people who spend 2 weeks in a dark room doing nothing else than developing films. It's like in the videos from or movies from the 70s with people standing in dark rooms. It's really lame. Then you ship these films to Japan, and some other student puts it under a scanning microscope and have to change this like every 10 minutes or so. So overnight. It's a rather time-intensive process. It took us a year to scan all of those. Then you need to run an algorithm to find neutrinos, so an event where nothing goes in and a bunch of particles come out. So some topology like this. And then you look if there is a muon inside, which would give you a track that essentially goes through the entire detector without re-interacting. Or if there's an electron inside, so that gives you an electromagnetic shower. You try to estimate the multiplicities of particles, the energy of the particles. So it's a very time-consuming process, but I will show you some pictures later. It gives you very much information. So in our first analysis, we saw 4 electron neutrinos and 8 muon neutrinos, which is pretty much what we expected. So each of them about a 5 sigma observation of those. So here's a picture of well, what the data looks. So this is a 1 by 1 millimeter area of in the detector. And all these colorful lines are muon tracks that go through. And okay, you just see lots of them. The color doesn't really have much meaning. And then after the search for neutrinos, we get this. So this is nothing comes in, a bunch of particles come out. Here you see a electromagnetic shower developing. So it's really looking for the needle in the haystack. So far, we have analyzed about 2% of the collected data. So there are many more results to come, many more data to be collected. This is the same event. There's a side view, and here is a sort of front view. So you see here you have an electromagnetic shower, so an electron recoiling back to back, a bunch of other particles. We can count them. So we have an electron ID. We can see that the denseness of the shower gives us the electron energy. For these particles, you see some of them scatter more. These are low energy particles. Some of them are very straight. These are high energy particles. So we can use the amount of scattering around as an estimate of the momentum. So really lots of information provided in there that makes it in the end worth to go through all this effort of reconstructing the events. This was, of course, then after we reported this observation mentioned in the news. And I personally like this one very much. This was a Viewpoint article written by Elizabeth Worcester. I never met her, but she called it the dawn of collider neutrino physics, which I like very much because I think this is true. It's this observation started a new field of physics, of neutrino physics, named at colliders. So some of the first measurements we did is to measure the cross-section of neutrinos at energies. So this has previously been measured as accelerators, so at beam dumps, up to 300 GeV. So this used the Fermilab beam that was to a target, and then at Newton for donut, the cross-section was measured. And then at very high energy, IceCube measured the cross-section. So they essentially used that for more than 10 TeV neutrinos. These actually get absorbed when going through the Earth. The cross-section is high enough that suppresses the flux, and they could use absorption to constrain the cross-section. But there was this TeV energy range left in between that we now can access with LHC neutrinos. And we have done the first couple measurements, both using the emulsion detector and using the muon appearance strategy. Can also, so this here assumes that we know the flux. Of course, we don't know the flux perfectly well, but then we can interpret it as a cross-section. We can also do the opposite and say that, well, assuming that we know the cross-section, but we actually know much better than the flux. This is just the perturbative QCD. The PDF uncertainties are in the sort of 5 to 10% region. Then we can use it as a flux measurement. And this is actually very useful to constrain forward particle production. So the neutrinos come from pion, kaon, and charm decays. And there are predictions of those, but these have never really been measured since, well, we don't have other experiments to really measure the production of forward particles. There's one other experiment measuring neutral particles, but these are charged pions, kaons. These have not been measured before, so it provides a very interesting test. And here I have two models. So this is my favorite prediction. This is EPOS LHC for light particles, and then we use POWHAG and PRISIA for charm particles. This is a favorite generator of our competing experiment of SND at LHC, and they used for more technical reasons, used DPMJet. We had long debates on which one should be used, and now we have data, and we can see that, well, DPMJet just predicts way too many forward charm production. So this is clearly in disagreement with the data we have. So we now know that this is not a good model. So we have already learned something that we did not know before. Before we could only speculate. Now we know that this model is in conflict with data. Of course, we can, with more data, we will be able to constrain these models much better if we have different neutrino flavors, more bins, also bins in rapidity. So multi-differential distribution, we will start to learn much more. One example for why this is interesting is QCD. So forward charm production can be calculated in perturbative QCD. So roughly speaking, you have gluon goes to charm, and one of the gluons needs to have a very high momentum fraction since we want to have a TeV energy neutrino come out. So one of the initial state patterns should also have TeV energy. So momentum fraction close to 1. The momentum transfer, I mean, the matrix element peaks around momentum transfer around the charm mass with something rather small. So then you can calculate that the other momentum should be, momentum fraction should be close to 10 to the minus 6, 10 to the minus 7 or so. So this region down here. So if you look in the QCD landscape, so momentum fraction versus momentum transfer, then, well, the collider neutrinos or charm production there probes both this region here and this region here, which is very interesting because here we mainly rely on old fixed target experiments, and here we don't have any data at all. So we can constrain, for example, the gluon PDF at ultra low X, where we start to expect interesting effects to happen. Like, for example, gluon saturation. The density of gluon gets so high that they don't only split, but that they also recombine, which will saturate the gluon density. And this is a line where we roughly expect this to happen. I mean, this is probably some phenomenological model. I'm not sure how reliable it is, but it's something that we may be able to see and answer questions in QCDs that have been around for quite a while. Here we might be able to say something about intrinsic charm. We might have gluon charm goes to Zener charm quark that is energetic, which is also a topic of debate that has been around since, I think, the 80s or so, has been around longer than I have. Okay, this is also interesting for astroparticle physics, actually, for two reasons. So the cosmic ray community, they talk a lot about the cosmic ray muon puzzle. So essentially, they see an axis of muons coming out of a cosmic ray air shower, which is about 8 sigma above what they would expect. And that's a big problem for them because what they really want to do is, constrain what is the composition of the cosmic ray. Is it proton or iron? And would tell them, where would they come from? Because different models of their production would predict different composition. But they see so many muons that the obvious conclusion would be that it's all uranium, which is also obviously nonsense. Cosmic rays are not all uranium. So they have studied that in great detail and found that probably an issue with the modeling of soft QCD at high energy, and they don't really have data in it. So yeah, what should they do? We studied one model of strangeness enhancement that is actually a very popular hypothesis. If you enhance the strangeness in cosmic ray air showers, you also expect to enhanced strangeness in at the LHC. This is a very extreme scenario, but could be less, which would change the neutrino flux from kaons and therefore our observations. So with measurements of forward parallel kaon production, we could actually provide crucial input to resolve the cosmic ray muon puzzle and ultimately learn where our cosmic rays come from. We also talked to people from IceCube. So what we call our forward charm production, they call their prompt atmospheric neutrino background. So neutrinos that come from charm decays in cosmic ray collisions. And in our first workshop on this, we invited Francis Halden, who said that, well, we don't have any good theory about it, and we don't have any data either. So we essentially don't know what we expect. With these forward collider neutrino measurements, we will be able to constrain this. Here's one example on, we essentially just plotted the PDF uncertainties on what they are now in NPDF and how this could be constrained, and then how this would change our prediction of the prompt atmospheric neutrino fluxes. And you see that it improved significantly. So this is why the astroparticle community is actually very interested in the collider neutrino program, because it provides important input. Okay. Also, if you think about LHC measurement, it provides input. So essentially, neutrino interactions at the provides the LHC with a neutrino ion collider. And I, of course, chose this name because it probably reminds you of the electron ion collider. It runs at a similar center of mass energy. One could do very similar things just using charge current interaction instead of neutral current interactions. For example, constrain PDFs via neutrino deep inelastic scattering. So this is a study here by Cruz Martinez et al. And this will help to reduce uncertainties for many LHC processes, for example, Higgs production, which would contribute to the legacy measurements of the LHC. So let me just provide a little bit of outlook on what we are thinking about now. So at FASER, it has been approved to run also 414, which will start hopefully in 2030 if there are no further delays. We are planning to continue the neutrino program doing the high luminosity LHC, and we are currently investigating plenty of options for how to upgrade the neutrino detector, including this one here. So this is a calorimeter that was designed by a university in China for the CPC. It has been used to, simply to test it. And these tests have been over, but we are now thinking about using this calorimeter and putting it close to the FASER location as an additional neutrino detector. I will visit, I think next week, my colleagues who are involved in this. So this will be very interesting. We're also thinking about trying to think bigger. So if you really want to see much more neutrinos, you need much bigger detectors. But bigger detectors is a problem since these side tunnels that we and our colleagues from SND at LHC are using, they were built in the 80s and are rather small and really not designed to host big experiments. So we have been working together with the engineers at CERN and came up with the idea of building a facility roughly here, so a little bit further away, still on CERN land, that would allow to have much bigger detectors, so bigger version of FASER, bigger version of the neutrino detector, but also, for example, a liquid argon detector to probe neutrino interactions, which would have very different design principles, very different systematics. And these could be tens of tons. So this would be 10, this would be 20 tons, so significantly boosting the event rate and allowing us to collect millions of these neutrino interactions, including, for example, thousands of tau neutrino interactions. This is a figure that I made where we applied the idea of FASER also to future colliders. So this is what FASER has pretty much collected now. This is what the forward physics facility at the LHC could collect. Here I show various old or proposed beam dump experiments. They are at lower energies, of course. You could also apply this to the FCC or equivalent in China. You would have, of course, higher energies and a much higher rate due to higher luminosities. Or you could apply it to a muon collider. There, neutrinos would come from the decay of muons, but since there are so many muon decays, actually the rate would be enormously high. So this has been studied in various papers and gives lots of interesting opportunities. So, for example, with a high flux at the FCC, you would even get a sizable number of neutrinos from heavy ion collisions. So you could study the production of these particles in heavy ion collision. Or you could, in both of those, study or imagine polarized targets, so similar to the compass experiment, and study polarized PDFs, for example. So even very sort of difficult measurements become quite feasible due to the high event rates. Just to give you a number here, the interaction rate for a ton detector would be somewhere in the kilohertz range. I mean, this is amazing. This is really, it's like the EIC, I would say. Yeah, this is HH. In EE, you wouldn't really get neutrinos, unfortunately. Yeah, this will probably, in the best case, happen after my retirement, unfortunately. Okay, let me conclude. So, following our original proposal of the FASER paper in 2017, a novel forward physics program emerged, which allows to more fully plot the potential of the LHC, both for new physics searches, but also for the collider neutrino measurements. So it's already quite successful. So we have seen the first neutrinos in over 50 years of collider physics. I think that's a nice achievement. And this is the way my colleague Jonathan Feng likes to see it. So this is just the beginning of a time of multi-messenger collider physics, which of course making an analogy to multi-messenger astronomy, where we see the neutrinos as a messenger to QCD to proton structure, and the new particles as a messenger to the dark sector. Here's a figure that I made summarizing this for the FPF, but it equally applies for FASER or SND at LHC if you want, to show the various aspects that could be probed from neutrino physics applications to QCD and astroparticle physics, and then the new particle and dark matter searches. So it has quite a variety of application that we did not think about when we wrote the first paper, but which emerged afterwards through also the nice input from the community. So I'm very happy and excited about this, and I'm sure that there are many more exciting results and ideas to come. So with this, I want to say thank you again for the award and for listening. And yeah, please let me know if you have any questions. So I'm just showing my colleagues from FASER. This was our last collaboration meeting.
Okay, thank you for your talk. Questions?
Two small questions on slide 48. You were showing the difference in the forward charm between SND at LHC and what you had.
Yeah.
What's the modeling difference? Is it something more like Pythia terms, or is it
I asked
something?
the author of this code. I mean, this was never used to model or never meant to model forward charm production. So the problem here is that the charm quarks are massless. So the distribution of charm quarks follows more those of pions, while you expect them to have a much broader transport momentum spectrum. So this is not at all surprising. We all expected this to happen, but it's of course a very clear example why I chose it, and one that we had quite a bit of debate beforehand. So.
And then 2 slides later, you were mentioning there's an 8 sigma discrepancy in cosmic ray. And then what is the blue line in the middle?
Okay, so here is a measurement that's I think that's PROG, yes. So this is, if you use the same model that predicts our baseline prediction here, then you would get a prediction that's significantly below the data. To get this, so this is something like the muon content in some units that don't really understand, I have to admit. To get it up to agree more with the data, you would need to boost the amount of strangeness quite a bit. So you would produce way more strange quarks than you naively would expect. But this would, if the same enhancement applies at the forward region of the LHC, then you would see this enhancement of the flux, which is like more than a factor 2. This is a very extreme scenario. Probably there is some non-trivial energy dependence that maybe if this is a factor, this effect, then maybe that's more like a 10% effect for us. But it's very model dependent, I would say.
So there is still a discrepancy. You just don't know where.
In cosmic ray, yes, there is still a discrepancy. It's not clear what this is attributed to. There's significant efforts in understanding it. We're, of course, not the only ones interested in this. The cosmic ray community is interested in it for probably a decade now, but as far as I know, it has not been exclusively solved yet. But they studied and are pretty convinced that it's some soft QCD effect. So new physics is very challenging because this is not the only observable. There are others, and new physics. In most scenarios that they studied, you would see that it also destroys agreement with other observations. For example, shower profile of the cosmic ray air shower. Which agrees well with expectations. So that's why they think strangeness enhancement is a good scenario, since it can solve this discrepancy but not destroy the agreement with other observations. And it's not surprising if this disagrees a bit. This is all soft, non-perturbative QCD. I mean, this is it's not like what we have heard about in the previous talk with like precision preservative QCD. It's more like black magic. Someone writes a model and no one knows if it's right or wrong, but we don't really know what to do either.
Okay, any other questions? So if not, let's thank our speaker again.